Welcome students to the Basic Electronics lecture series. Today we are going to take the fourth lecture in which we want to discuss diode approximations. So let's straightforward go to the contents of the lecture. As you can see on the screen, our today's topic is diode approximations. Now we should have a question, why should one use diode approximations? Why do we require it? So the diode, while construction, it is in the process of doping level of impurities. So when different impurities are added, there might be a possibility that at very high temperature in the vapor form, there is a slight variation in the doping. For example, we are constructing 50 diodes of similar characteristics or similar category, but there is some variation in the doping level while manufacturing. So it might cause some slight variation in the physical size of diodes also. So due to this slight variation of size as well as doping level of impurities, similar kinds of diode will behave differently. How they would behave differently? Their characteristics will vary slightly. Their Imax, maximum DC forward current, may be different. Their power rating may be different. Their reverse breakdown voltage may be different. And so many changes may be there. That means due to this variation, your similar diodes may behave differently. So under such circumstances, what we need to do? If we want to analyze them, then we need to approximate the diodes. That if diode gives such kind of reading, we will assume that it is forward biased. If it gives a typical kind of reading, then we will say it is reverse biased. So that's why we require diode approximations. So you can say diode approximation will give you behavior of diodes. And there are three types of diode approximation. The first approximation is called ideal diode. Ideal in the sense, the diode does not have any detailing. That means if your ideal diode is forward biased, it will give you zero resistance and infinite current. And if your ideal diode is reverse biased, it will give you infinite resistance with zero current. So why ideal diode behaves like this? Because there is an approximation that ideal diode does not have any barrier potential as well as no bulk resistance. So that means ideal diode does not have barrier potential of 0.7 volt as well as it also does not have bulk resistance. It is just ideal. So how it will be in equivalent circuit? Suppose this diode is ideal. So if you forward bias, it works as closed switch, zero resistance, infinite current. And suppose you reverse bias it, it works as open switch with infinite resistance and zero current. So this is called ideal diode, which is practically not possible, but it is just first approximation that if your diode is ideal. So if your diode is ideal, how will be its VI characteristics? So it is quite easy to judge. If your diode has slightly greater than zero voltage, your current will be immediately infinite because diode is fully forward biased and it carries maximum current with zero resistance. So current is almost infinite, and because it is working as short circuit, closed switch, so zero voltage. And if you reverse bias, then diode will have infinite resistance but zero current. So that's why in reverse bias the current will remain zero. So what does the VI characteristic say? Ideal diode has infinite current and zero resistance in forward bias, zero current and infinite resistance in reverse bias. It is just ideal. So we should have a question, where should we use this approximation? Who will use it? So such kind of approximation will be used by the people who are doing troubleshooting of any problem, circuit problem, or they are doing quick analysis of any circuit. Suppose you want to roughly analyze any circuit, by overview, then you can use first approximation, whether the circuit works or not. Likewise. So ideal approximation or first approximation is used by the people who are doing troubleshooting or quick analysis of the circuit. Now let's go to the second approximation of diode. Now as I told, ideal diode does not have any detail, but the second approximation diode has some detailing. Now what is that detail? In this case, we assume that our diode has barrier potential of 0.7 volt, but no bulk resistance. That means second approximation diode has barrier potential present, but there is no bulk resistance. What do you mean by bulk resistance? That we discussed in last lecture. Total ohmic resistance of P region and N region, which is called bulk resistance and which is very small, around 1 ohm. So in ideal diode, there was no barrier, no bulk resistance. In second approximation, we assume that there is barrier present over here, but there is no bulk resistance. So how will your diode behave? If your input voltage or input diode voltage is greater than 0.7 volt, diode will be forward biased and the diode conducts fully with maximum current. But there is no bulk resistance, so that means there will be no drop across diode. So that means then after diode current increases but the voltage remains 0.7 because there is no extra drop across diode in the absence of bulk resistance. So only 0.7 will be the voltage of diode, but the current will increase indefinitely in forward bias. And if you reverse bias by applying less than 0.7 volt, it will provide you zero current and infinite resistance. So how will be its equivalent circuit? Suppose this is our second approximation diode. So if you forward bias it, it works as a closed switch with maximum current and barrier potential of 0.7 volt in series. And if you reverse bias it, it will work as open switch with zero current and in series with barrier potential of 0.7 volt. This is second approximation of diode, in which there is some detailing of barrier potential. So how will be its VI characteristics? It will be slightly different than ideal. Just see what is the difference. The ideal diode was operating after zero voltage because there is no barrier, but in this case there is barrier of 0.7 volt. So when your diode voltage reaches 0.7, after that diode is fully forward biased and it carries maximum infinite current. And after that, if you increase the voltage, current will increase, but voltage will remain 0.7 because there is no bulk resistance. So though no ohmic drop will be there. And if your input voltage is less than 0.7, diode remains reverse bias, current is zero, resistance is infinite. So this is VI characteristics of second approximation of diode. Who will use it now? So it has got some detailing. That's why it will be used for some more detailed work. So such approximation is used by technician level. That means you can say ITI people. ITI people generally what do? They repair the circuit. They try to work it out whether it is working properly or not. They are trying to find the faults on somewhat detailed level. So that's why they will use the diode approximation as second approximation and not the ideal one. Let's talk about the third approximation. It will have some more detailing. What is that more detail? In this case, we assume that diode has both barrier potential of 0.7 volt and bulk resistance also is present. That means it has got more detail than second approximation. So now you can imagine how it will work if your input or diode voltage is greater than 0.7, diode will be forward biased and the diode conducts fully, and then after what will happen? Because there is bulk resistance present, there will be a drop across diode, IDRB. So that means then after if you increase the voltage, the current and voltage will increase linearly with each other. That means the current will not become infinite, but the current and voltage will vary linearly with each other after 0.7. And if your voltage is less than 0.7, diode will remain reverse bias with zero current and infinite resistance. So now in this case, your diode voltage is not only 0.7, it has got some drop of bulk resistance. So that's why diode voltage in third approximation can be written as Vd is equal to 0.7 plus there is some drop due to bulk resistance. Whatever current passes through diode multiplied by diode resistance, that is bulk resistance. So now how will be the equivalent circuit? Suppose this is my third approximation diode. So when I forward bias, it works as a closed switch maximum current in series with barrier potential of 0.7 volt in series with bulk resistance, which is around 1 ohm, less than 1 ohm. And if I reverse bias, it works as open switch in series with barrier potential of 0.7 volt and in series with bulk resistance. So in reverse bias, as you know, diode has got much more high resistance. So in that case, if bulk resistance and reverse bias resistance are at least 100 times comparable than each other, then you can neglect RB, bulk resistance. Suppose RB is 1 ohm and reverse bias resistance is 200 ohm, then you can neglect RB because it is very much higher. But suppose RB is 1 ohm and reverse bias resistance is 50 ohm, then you cannot neglect this. You will consider total resistance as 51 ohm in reverse bias. So that is all about equivalent circuit of third approximation of diode. Now let's see the characteristics. So it is somewhat different than 2D, that is second approximation. What happens in this case? When your voltage is greater than 0.7, diode is fully forward biased and it conducts maximum current. But when the current increases, voltage also increases linearly due to bulk resistance IDRD. So your diode voltage was 0.7 plus IDRD. So this is forward characteristics. If your diode voltage is less than 0.7, it remains reverse bias, zero current, very high resistance. So this is VI characteristics of third approximation diode. Now it has got more detailing, so that's why we will use it. So it will be used by very high level analysis. Third approximation is used at very high level analysis, or you can say engineer level analysis, because any engineer has the main duty of design of system, whether it is mechanical, electrical, electronic, computer or IT. Engineer has to design something and it has to design in such a way that it has to take all the detailings. That's why third approximation of diode will be used at high level analysis, or you can say engineer level analysis. So all these three approximations will be further clear when we take some numerical examples. So look at the first numerical. Suppose a diode has power rating of 8 watts and it carries 4 ampere current with voltage drop of 1.5 volt. Then you have to find power dissipation of diode and you have to state whether the diode will be damaged or not. So just list out what is given. You are given power rating. So I told you in last lecture what is power rating of diode. Maximum power which the diode can handle. So it is given as 8 watt. That means P max is 8 watt. Diode voltage is 1.5 volt. Diode current is 4 ampere. Let's find out power dissipation of diode. PD is equal to VD ID. 1.5 into 4, that is 6 watt. So that means our diode consumes 6 watt power, or you can say dissipates 6 watt power. So you have to answer whether your diode will be damaged or not. So it is a matter of common sense. Your maximum power capacity of diode is 8 watt, but right now it is dissipating 6 watt. That means it is safe. That means we can say here dissipated power is less than maximum power, so diode will work properly and it will not get damaged. I hope it is clear to all of you. Let's see another example. Just see this circuit. It has 5 elements, 3 resistances, out of which one is load resistance 1 kilo ohm, 1 DC battery and 1 diode. Now what you have to find for this circuit? For the given circuit, you have to find load voltage, load current, load power using ideal diode, second approximation diode, and third approximation diode if bulk resistance is 0.23 ohm. That means we have to use the same circuit for ideal, second, and third approximation. So before applying all the approximation, we need to simplify the circuit because we are interested in load voltage, load current, load power. So this particular thing will not be changed, but look at this initial part of three elements. There are two resistors and one battery. So if you want to simplify complex circuit having more than one energy sources and more elements, we can apply Thevenin's theorem, which you studied in physics. What does Thevenin say? He says that any complex circuit can be replaced by only two elements. So after simplification, your complex circuit will have only two elements, one voltage source in series with one resistance. So that means after simplifying these three, we will get only two elements, one battery in series with resistance. Battery is called Thevenin voltage VTH and resistance will be called Thevenin resistance RTH. So that's why I want to highlight this portion. Suppose I have highlighted the portion and I want to apply Thevenin's theorem on this particular circuit. So forget about this. They are not included in Thevenin. We are just using this circuit. So you can say this is source of energy and the end terminal is called load. So after simplification, as I told, what will you get at the end? One battery VTH in series with one resistance RTH. But how to find VTH and RTH? So Thevenin says VTH is nothing but open circuited load voltage. VTH is open circuited load voltage. That means whatever voltage you measure across 3 kilo ohm. So now using voltage divider, it is quite easy. What will be the voltage across 3 kilo ohm? Thevenin voltage VTH is equal to voltage across 3 kilo ohm. What is the voltage divider? 3 kilo ohm upon 3 kilo ohm plus 6 kilo ohm multiplied by input voltage. 3K upon 3K plus 6K multiplied by 36. Our answer will be 12 volt, which is called VTH. Now how to find RTH? How to find Thevenin resistance? So Thevenin says that whatever energy sources are there in your circuit, just replace them by their internal resistance. Now luckily our circuit has only one energy source and it is voltage source. So you need to remember voltage source has zero internal resistance ideally and current source has infinite internal resistance ideally. So that means zero resistance represents short circuit and infinite resistance represents open circuit. So in this place, if there were a current source, we have to open circuit, but here it is a voltage source. So if you replace it by internal resistance, it will be just replaced by a short circuit. So just imagine if I make it a short circuit, what will be left in the circuit? If I short it, there will be two resistance left. And what will happen to them? Both of them will come into parallel with each other, like this. Both will come in parallel with each other. So what will be their equivalent? 6K into 3K upon 6K plus 3K. Answer will be 2 kilo ohm. This is called RTH. So we get both the VTH and RTH. So let's replace this dotted portion by simplified circuit. What is the simplified answer? VTH 12 volt in series with RTH 2 kilo ohm. Remaining elements are as it is, diode and load of 1 kilo ohm. So this is our final simplified circuit ready for the approximation. I hope it is clear. Dotted portion is now simplified. Now let's apply ideal diode. So as you all remember in this particular lecture, what is ideal diode? If it is forward bias, it is short circuit. If it is reverse bias, it is open circuit. So due to this battery polarity, diode is supposed to be forward bias. So let's replace it by short circuit. VTH as it is, RTH as it is, load as it is. So they form a closed loop. Now let's find the load current using KVL in a closed path. So you find that there is only one battery or energy source, which is voltage 12, and there are two resistors 2K and 1K, both are in series. So what will be load current? V by R, 12 volt upon 2K plus 1K. Answer is 12 upon 3 kilo ohm. Load current will be 4 milliampere. Kilo goes in numerator, it becomes milliampere. So that's what we got as load current passing through load. Now what will be load voltage? So according to Ohm's law, V is equal to IR. So VL is equal to IL into RL. IL just you got 4 milliampere. What is RL? 1 kilo ohm. Kilo and milli are cancelled. 4 into 1. Load voltage is 4 volts. Let's find load power. P is equal to V into I. So PL is equal to VL into IL. 4 volt into 4 milliampere. Load power is 16 milliwatt. Let's try to find out one extra parameter, which is diode power. PD is equal to VD into ID. Now because our diode is ideal, so that means it has no voltage because it is short circuit. So 0 voltage. So 0 voltage multiplied by 4 milliampere, answer is 0 watt. So what does it indicate? Ideal diode does not use any power. Our ideal diode uses no power, which is practically not possible, but it is ideal. Now let's apply second approximation. So all of you remember that in second approximation, diode is forward biased, then it is a closed switch in series with barrier potential of 0.7 volt. VTH as it is, RTH as it is, load as it is. We have just replaced the diode by second approximation. Now let's find out the load current in the loop. Now there are two batteries, but if I move in clockwise direction, I come out of plus terminal of 12 volt and I come out of minus terminal of 0.7. That means both the batteries are opposite. So what will be the net voltage? 12 minus 0.7. What is the total resistance of the loop? 2K plus 1K, 3K. So your answer will be 11.3 upon 3 kilo ohm. Load current is 3.77 milliampere. What will be load voltage? VL is equal to IL into RL. 3.77 milliampere into 1 kilo ohm. Milli and kilo are cancelled. Load voltage is 3.77 volt. Load power PL. VL into IL. 3.77 milliampere into 3.77 volt. My load power is 14.21 milliwatt. Just look at the answer of second approximation. In first it was 16 watt milliwatt. Now here it is 14.21. That means we are going nearer to the actual answer. Ideal answer was not real. Now the second approximation is more nearer to real answer. Diode power. What will be diode voltage in second approximation? 0.7 volt. So let's put 0.7 into IL, that is load current. 0.7 into 3.77 milliampere. My diode power is 2.639 milliwatt. Earlier it was showing 0 in ideal, which is not possible. So now we are nearer to a real answer. Let's go further and use third approximation. So in third approximation, bulk resistance is also present, 0.23 ohm. So what will be the diode replication? VTH as it is, RTH as it is, and forward bias diode is short circuit with barrier potential of 0.7 volt and 0.23 ohm bulk resistance. Load is as it is 1 kilo ohm. Let's try to find out load current in series. What is the net voltage? 12 minus 0.7. What is the net resistance? 2K plus 1K plus 0.23 ohm. So let's convert this into kilo ohm. So this is 3K plus 0.00023 kilo ohm. So your load current will be 3.7663 milliampere. Earlier it was 3.77 milliampere. Now it is 3.7663 milliampere. So it is more detailed now. It is perfect answer. Now let's find out load voltage. VL is equal to IL into RL. Load is 1 kilo ohm. So our answer will be 3.7663 volt. Load power, PL is equal to VL into IL. It will be 14.185 milliwatt. Now you can see it is more detailed answer compared to the second approximation. Earlier it was 14.21. Now it says 14.185. Because detailing is high, so our answer is more nearer to accurate answer. Diode power PD is equal to VD into ID. So if you can remember, in third approximation, due to presence of bulk resistance, diode voltage is not only 0.7. Plus there was a drop ID RD. So let's put the values 0.7 as it is, plus what is diode current? Load current, because all of them are in series. So whatever is load current, same is diode current. RD means bulk resistance. So 0.7 plus 3.7663 milliampere into 0.00023 kilo ohm. So your simplified answer of diode voltage will be 0.700866 volt. So let's try to find out diode power. PD is equal to 0.700866 into load current, that is 3.7663 milliampere. So diode power comes to be 2.6696 milliwatt, which is a more detailed answer. So in summary, what we can say? Ideal approximation diode has no barrier potential, no bulk resistance. Forward bias means maximum current, zero resistance. Reverse bias means zero current, maximum resistance. Second approximation diode has barrier potential but no bulk resistance. And third approximation diode has both barrier potential as well as bulk resistance. So this is all about today's session. We will meet with another contents in next session. See you then. Till have happy learning.